All right, yeah, I'm ready as well. So let's begin. Hello, everyone. On behalf of ISI Bangalore students and research scholars, I welcome all of you to the first session of day 5 of the Limit Camp. Today, we have with us our speaker, Oishee Banerjee. She did her BMath from ISI Bangalore, Masters and PhD in Mathematics from University of Chicago, postdoc from Hausdorff Center of Mathematics, Bonn, and Institute of Advanced Studies, Princeton, and is now an assistant professor at Florida State University. She works in topology using techniques from homotopy theory, sheaves theory, and algebraic geometry to understand the topology of moduli spaces of algebra geometric origins. We are very honored to have her here for her talk titled Topology Knows Arithmetic from Betty Numbers to Point Counts via Weil Conjectures. I would like to remind everyone to keep the microphones off during the talk. If you have any questions, please ask it in the chat. After the talk, you can ask questions. This talk shall be recorded and uploaded to our YouTube channel, so please check it out if you need anything. I would like to hand it over to the speaker now. Thank you to Oishee for being with us today.
Thank you to the whole Limit team for this invite, for allowing me to be, for inviting me to be a part of this amazing endeavor. This really means a lot. And I want to say something that one of the biggest advantage and sometimes the disadvantage of mathematics is that there are a lot of proper nouns. And I will be using words which you may or may not know, but please do not let yourself get bogged down by those nouns. I'll try to say a few words about each word I use, but if it seems gibberish, just like let it go and try to see if you can sort of capture the idea and ask me questions whenever. And thank you again for the invite. Okay, let's begin. So let me start with a prologue, which is about coincidence, coincidence, in arithmetic and topology. So here is a geometric object that everyone loves, and for very good reason, which is elliptic curves. And let's take one such example. Let's take something like this as a polynomial. A and B, let's say, are maybe integers. And we just impose a condition which is called the discriminant being non-zero, which amounts to saying that this quantity is non-zero. Let's assume that. Okay, so this sort of object has, or can be thought of as having two incarnations. In say, if you know some things about Riemann surfaces, you would know that this gives rise to a torus. More specifically, something like a C modulo a lattice. This lambda lattice, so something isomorphic to z to the 2, and it looks like exactly how you would expect a torus to be, so something like this. How is, if you don't know how, if you haven't seen how this guy gives rise to this, let me say a few words about how to see it. If you think of the complex valued solutions to this polynomial, then, well, so you would be like plotting this in like C2. Let's say the x-axis is for one complex number, the y-axis for another complex number. And so this will be like a complex one-dimensional geometric object. And being complex one-dimensional means like real two-dimensional. So you would expect something like a surface. And but this surface is specifically this one, it tends to be like a part of a graduate course on complex analysis, but it can be seen reasonably easily as well. If you take the zeros of this polynomial, suppose the zeros are you sort of like make some transformations of the polynomial, and suppose you reduce the zeros to be 0, alpha, beta, and something else, let's say the point at infinity. Then you would, the typical sort of construction is that you do what are called branch cuts. And these are called branch cuts. You take two copies of the sphere, these two are spheres, and you make these cuts, and you glue them together along the cuts. Zero infinity, alpha, beta, 0, infinity, alpha, beta, and you glue these two copies together, and you get back the torus that I claimed that you get. The two copies are coming from, you can think of them as this polynomial. Like each value this takes, you get two values for y, right? So you get, like, for each value of x, unless it's one of these zeros of that polynomial, you get two distinct values of y, so which is giving you these two copies, and you're gluing them together along these what are called branch cuts, which is literally the mathematical term for that. So gluing along branch cuts. If you're not familiar with this branch cut technique, just take it on faith that this guy is a complex one-dimensional geometric object, so it should be a real surface, and the surface, one can prove, looks exactly like this. It looks like a donut. So that's about the complex solutions. What about the finite field solutions? So we will, whenever I write fq, we will take q to be a prime power. So some like p to the d. And fq is a finite field corresponding to that. And if you look at fq solutions, there is this famous theorem by Hasse, which says that if I call this, let's call this geometric object something E, then the number of points, so fq is being a finite field, it's a finite set. And this object, this equation, can have only finitely many solutions in fq. So this is going to be a finite number in that case. And there is this famous theorem Hasse, which says that this has a bound. This is bounded by q plus 1 minus 2 square root of q on one hand, and q plus 1 plus 2 square root of q. Okay, fine. So far, this discrete set with its finite number of points seems to have nothing much to do with this donut here. So the question is, am I just sort of like screaming in the air for some sort of connection, or is there really something going on? And that something is indeed going on is an observation from like what, 1940s now, which is more than 8 years ago. And let me sort of make a heuristic about what that connection looks like. So that's the this torus has the property that its cohomology or homology are well known. If you don't know what cohomology and homology is, it's essentially encoding, like the zeroth cohomology is supposed to encode the number of components. The first cohomology, sort of like the first and higher cohomology, they encode like the possible holes and the dimensions of those holes. It's a well-known fact that the rank of the zeroth cohomology of E is 1. It's a like say as a rational vector space, it's just Q. It's a one-dimensional vector space over the rational numbers. The rank of the first cohomology, let me write Q, is 2, and the rank of the second cohomology is yet again 1. If you again don't know what cohomology is, just sort of like think of these as encoding the fact that this torus has just one connected component. So that's the H0 being 1. And for H1, the rank being 2, it has two special loops. One is like this, and the other is like this. These two loops generate the first cohomology, and the second cohomology being rank 1 means that sort of like all points on this torus are same up to transformations. So with that in mind, now note that here's a heuristic. We can write maybe if that's, so let me put this equality within like emphatic quotes, that this is as if it's a sum over Q to the maybe times some constant values, Q to the dimension, so that's a complex dimension of E, minus I over 2, where I is ranging from 0 to 2. So what would that look like? This would look like something like C0 Q to the, well, dimension, the complex dimension is just 1, so that's Q, plus C1, some square root of Q, plus C2, right? When you plug in various values of I, and you plug in the complex dimension of E being just 1, this is the sort of estimate you get, which looks an awful lot like Hassel's bounds, right? So we observed, not just from this example, but many situations of like many algebraic geometric objects, algebraic varieties, that the something that entirely lies in topology gives reasonably close finite field estimates, the number of estimates for the number of finite field points of an algebraic variety. And so the upshot of this prologue is that Weil, famously sitting in a prison in France back then, well, let's record in prison, because that's something. What on earth is going on? I'm definitely not quoting Weil on that, because he had far more insights than what I'm talking about right now. But that's sort of this is sort of the thematic tone that this whole talk is going to have. Okay, so let's explore this what is going on through some more examples. Any questions so far? Okay, so Act 1, I'm going to call it A Tale of Two Worlds, topology, or maybe I should say arithmetic and topology. Great. So let me talk about a space which sort of brought topologists into these sort of connections between number theory and topology. Speaking as a topologist myself, let's ask this question first of all. So let's focus on the arithmetic side for a moment. here's a question. How many square-free integers are there between n and 2n? Well, to answer this question, one of the first things that we can naively do is that, well, if some integer is square-free, it's not going to be divisible by 2 squared, 3 squared, 5 squared, prime squared, and so on. So being square-free implies, so n being square-free implies n not divisible by 4, 9, 25, p squared, and you go through all the primes. And it is not unreasonable to expect that not being divisible by p squared, like the events that n is not divisible by, say, p1 is one of the primes, p1 squared, and p2 squared, p1 not equal to p2, are independent events. Being not divisible by 4 and being not divisible by 9 should be independent events. So you would expect in that case that the probability of this happening is like 1 minus 1 over 4 times 1 minus 1 over 9 times 1 minus 1 over 25, and so on, running through all the primes. If you have seen a zeta function before, then you immediately know what this looks like. This is zeta 2, the Riemann zeta function, inverse of that. If you haven't seen the formula for a zeta function before, never mind, just take it on faith that this is what it looks like. Maybe it's not a bad idea to record this, that one way to define the Riemann zeta function is this expansion over n. And yeah, you plug in s equals 2. And if you multiply, if you use the fact that every integer is a product of its primes, you would get this expansion, what's called an Euler product. Okay, so this is all about the probability of an integer being not square free, of an integer being square free, sorry. And if we want specifically how many there are between capital N and capital 2n, how many integers there are that are square free, we would be looking at this. So suppose SFN is the number of square free, SFN, number of square free integers in this interval n and 2n, then we are looking at, so asymptotically, this would be limit n approaching infinity. So there are capital N integers between n and 2n, and you want to find out how many of those out of these n are square free. So that would be this quantity. That would be this quantity. And this should be asymptotically just zeta to inverse, right? Okay. So how about, so here is a modified question. How about, instead of asking for square free integers, so let me say, square free in Z, we ask the same in another PID, which behaves an awful lot like the integers, which is the polynomial ring in one variable, FQ square bracket X. So that's just all polynomials over FQ. And you're asking about square-free polynomials in it. So with that in mind, so that seems like a legit question. If we replace, so some replacements are happening now. So instead of Z, we take FQX. What about the notion of an interval in Z? So Z is totally ordered, so we could talk about like integers being between capital N and capital 2N. What is the correct analog of that? Well, if you think about it, saying that an integer is between n and 2n is basically claiming that, like, if capital N is positive now, you're saying that the absolute value is between capital N and capital 2n. And this would mean that the analog is that, so here is a notion of an absolute value on the ring of polynomials, which is q to the degree of the polynomial. So let's define this as the absolute value. Now, the absolute values that these polynomials take is a sparse set. It's q to the z. Such absolute values lie in q to the z, which is sparse. So effectively, instead of asking some polynomials with absolute values between some range, you can just like specify, like fix a degree of the polynomial and ask how many monic square-free polynomials there are in that degree. So in effect, ask how many monic square-free polynomials of degree, let's say, of degree n are there in FQX. Right? That's a reasonable question. And if you think about it, the finite field FQ is not algebraically closed. So it's not like you can claim, oh, if like x minus alpha, like in degree 2, suppose x minus alpha times x minus beta, where alpha and beta are two distinct elements in FQ, those are just these square-free polynomials. You cannot claim that because you can have some polynomial, some quadratic polynomial in FQ, let's say, which has no zeros in FQ whatsoever, but it has some zeros in the field extension of FQ. And turns out that in that field extension, it ends up having no repeated roots. It ends up being square-free. So this is observed that this is not something that you can detect. Not something you can detect by just considering roots of polynomials in FQ, because FQ is not algebraically closed. So we have not only asked a well-posed question, we have also documented the nuance, the obstacles that would come up in a if we try a naive method like we did for integers, to detect the square freeness of polynomials in FQX. Okay, so what do we do? Where am I? Right. And so if so n itself, it's then if we fix a degree, then we are replacing n by q to the n. We are fixing the absolute value of the polynomial. So we are fixing the degree of the polynomial, and so the absolute value is q to the n. So between n and 2n, we are fixing now just capital N and asking how many square-free polynomials there are. And so q to the n is the replacement of capital N. So previously, for square-free integers, we wanted to know this limit. Was the goal. And now we want to understand this limit, q to the minus n. Let me write s of q little n. Right. So first of all, this limit, here's a fact, this limit exists. And not only does it exist, one can show, and there are several ways to show it, but one can show that this guy here is actually equal to 1 over 1 minus q. And we will come to this quantity. It might seem like something I've thrown out of the blue, but we'll come to this in a moment. Okay, fine. Let's take it on faith that let's for the moment take it on faith that this limit indeed equals 1 over 1 minus q. Does this quantity look at all like what the previous answer we had, which is what this inverse of a zeta function? Apparently not. Doesn't look like it on the nose, but it is. How do we see that? So the dissimilarity is, in fact, superficial. What you can do is play the same game as you did with Z, in which case you would be writing limit n maps n goes to infinity q to the negative n square-free polynomials of degree n equals product of 1 minus absolute value of p to the negative 2. P is a prime, but prime in what? It's a prime in FQX now. So these are irreducible polynomials over FQ that you're looking at in one variable. And recall that this absolute value is nothing but q to the degree of the polynomial p. I've used p for a prime before, but now I'm using it as a prime in FQX in a polynomial ring. Okay, so one can then show that this guy actually equals a zeta function as well, but it's a zeta function of this form. So what is quite astounding is that this guy, which is a priori an infinite product, is not just a mere infinite product, but it converges to a legit rational function. So here is the miracle. the zeta function converges. In fact, it is a rational function in Q. This miracle is yet again something that Weil conjectured, and we'll see some of those statements a bit later, but this is something to be recorded. Okay, so in effect, what we have obtained is that out of the q to the n, so the number of degree n polynomials, monic degree n polynomials in FQ is q to the n, and out of those, q to the n minus 1 would be the square free ones, right? So this is the total number of degree n monic polynomials in FQ, and it seems that out of them, these many are square free. Okay, so far everything seems to be just like brute force algebra with a bit of like conceptual probability, let's say. And this sort of thing is not a proof, but classical analytic number theorists know very well how to prove these just using these Euler product techniques. Okay, so let's change gears, and I promised a tale of two worlds. So let's take a look at topology. We can ask a similar question about polynomials being square free, but not over C, not over FQ, not over the finite fields, but over C. Not exactly. I mean, over FQ, there are going to be finitely many square free polynomials. Over FQ, there are finitely many polynomials of a fixed degree. So of a fixed degree, the square free ones is also going to be finite. Over the complex numbers, you cannot possibly hope to have finitely many square free polynomials in any fixed degree. So that kind of that sort of finiteness issues just goes out of the window. Nonetheless, it is a topological space. Nevertheless, you can claim that. Let capital P, is that a bad word? No. Let F n C be the space of all monic square free polynomials of degree n. Now, the complex numbers is an algebraically closed field. So every square free polynomial you have, they're going to have n distinct roots. Every degree n monic square free polynomial you're going to have, they're going to be n distinct roots. So that is going to account for like c to the n. Then you subtract all the diagonals, right? Because you're looking at those that have distinct roots. And then you go modulo the symmetric group action. Let me write sigma n for, so this is symmetric group. Okay, so that seems like a topological space in like an ambient CM sort of, and it's very, very, very far from discrete, from being discrete. But being a topological space, you can ask what its homology and cohomology groups are. I mean, you can be interested in other topological properties like fundamental groups, etc. It was quite an interesting and groundbreaking result of Arnold. I think it was in 1969 or 70. Let me write just 70. That the zeroth cohomology of this space, let me just take rational coefficients. So this is just Q. And the first cohomology is also Q. And anything bigger vanishes. If you're not familiar with these notations again, let's just think of it in the following way. This is some topological space sitting in C to the n, and one is essentially counting holes of a permissible range, and that's pretty limited. Uh, this is the first line reflects the fact that this is a connected topological space. One, that's non-trivial thing to show. The second thing reflects the fact that like the holes are also pretty limited and there are no higher dimensional holes, so to speak. Okay, now if we sort of follow the previous heuristic, which is very, very loosely phrased and far from being accurate, but nonetheless a heuristic, you would be getting something like this. So one can show through a non-trivial amount of math, amount of techniques that were developed to prove Weil conjectures. Purely from the information on the cohomology, one can show that the number of, so this number, so the number of square free polynomials of degree n is q to the n minus q to the n minus 1. And to show this, one can entirely, like this is something that one can show without any knowledge of zeta functions whatsoever. One only needs to know, first of all, the topology result of Arnold with just a tad bit more algebra geometric information, which is called Galois representations. And I'm just going to throw the word out there as a proper noun to be Googled by you if you're interested, or ask me questions out of the talk. But Arnold plus this non-trivial amount of techniques that were developed to prove Weil conjectures can be summed up as Grothendieck's yoga of weights. That's the buzzword that gets behind sort of transforming Arnold's result into an actual concrete point count. And in the particular case, when we are looking at the topological space of square-free polynomials of degree n over the complex numbers, these weights are surprisingly simple to compute. So one only needs to understand first the singular cohomology of this topological space and just a bit of information about weights. That's a little bit of non-trivial part from Weil conjectures, and one immediately gets that the number of square-free polynomials of degree n over a finite field fq is q to the n minus q to the n minus 1, and then the proportion of, so if you divide this by all monic degree n polynomials over fq, that's going to be q to the n minus q to the n minus 1 divided by q to the n, because there are q to the n many monic degree n polynomials over fq. So that's going to be 1 over 1 minus q. And that is the right count we obtained previously through the Euler product, through mimicking sort of what analytic number theorists has done in the past. So if this is not a major coincidence to explore, I don't know what is. And this would lead me to the next act of the play, which is now finally a moment where we should at least look at zeta functions with some degree of concreteness. So that's what I'm going to do now. Any questions so far? So takeaway, topology plus, let me just write weights within quotes, gives arithmetic info. I forget the quote of Weil, which I noted down at some point. Well, I forget the quote. Maybe I'll remember at some point. Okay. So act 2, not 3. Zeta functions. Or the mantra for us should be all roads lead to zeta functions. Of course, people are going to argue with that statement, but who cares? Okay, so let X be, I would prefer not to use scheme theoretic words. So one can say it's a scheme over Z. So let's think of it as, let X be an object, a geometric object cut out by polynomials with integer coefficients. For such an object, if you look at the zero loci of these integer coefficient polynomials, you can go mod FQ. You can go mod Q. So look at solutions mod Q, where Q again is p to the n for some n, p prime. Prime in Z, not a prime in some other PID. Let me denote this set to be XFQ. One can also look at things like solutions mod like Q to the n, where Q is a prime power, but you take higher and higher powers for that. Not everything should be little n, Z, suppose. Okay, solutions mod Q to the n, and we would denote that set by XFQ to the n. It's a standard fact in field theory that if you have a finite field, all field extensions are given by like relevant powers of that. So these are finite fields, these are extensions of this guy, and we are looking at solutions in those fields. And the zeta function, the Weil zeta function is the following. It's defined as an exponential. I'm just going to write down the formula here just to have something concrete here, but we're not going to directly use this formula for anything. So that's the definition. And if you just do a bit of like get your hands dirty and do a bit of algebraic checking, you would see that if you take X to be, if you know what the word affine line means, then this is gonna be just like this cardinality is just gonna be Q to the N. And so if X is like spec of FQ of little x, so X is that geometric object whose ring of functions is the polynomial ring in one variable over FQ, then plugging in and if we replace t by q to the negative s, then we get back the zeta function we had before. From Act 1. This was a zeta function which came up at s equals 2 when we were looking at square-free polynomials over FQ of degree n. And this is a more general version of that, which specializes to those sort of zeta functions. And the generalization is vast if you think about it, because X is just about any geometric object, not just a like a one-dimensional field object. Okay, so Weil conjectured that, and looking through the past talks in the series, I saw that there were some amazing talks on Weil conjectures before, which is fantastic because it never hurts to see fantastic ideas come up again and again and again, and Weil conjectures are definitely one of those. So Weil conjectured, I'm not going to state all the conjectures, but I'm just going to say a few words about some of the things that are pertinent to the goal of my talk. So one of the things he conjectured is that this guy, ZXT, is a rational function in like Q to the negative S. If you think back to what we did in Act 1 about square-free polynomials, we used zeta function, but like we didn't exactly compute anything with the zeta function, but we did find out that topology says that 1 over 1 minus q should be the value of zeta 2. So the zeta function in that case is indeed a rational function in Q. So one of the things that Weil conjecture says is that it's not just for square-free polynomials, but it's for many other geometric objects, namely any scheme over finite fields. And not only is this a rational function, the conjecture also mentions that it has a very concrete formulation. It looks something like a bunch of polynomials in T indexed by some odd indices for some reason. And so Weil conjectured that there are polynomials that are evenly and oddly indexed in a very precise fashion for a very good reason, and they look like that. And I'll say a few words about what these polynomials are supposed to be in like 5 minutes or less than that. Then there is the part about that the conjecture has satisfies some functional equation, and there is a corresponding Riemann hypothesis for this. And I'm not going to touch upon those, as fantastic and as interesting they are. Time is limited. I want to say a few words now about this PI, these polynomials. These are the polynomials which deeply reflect this x that we have taken as our choice of a geometric object. It's cut out by some polynomials with integer coefficients. We can go modulo prime powers to get these guys. But what we can also do is we can, I'm going to draw another weird arrow somewhere and make a mess out of it, but it needs to be written. We can also extend scalars to see and look at the complex valued solution of this, right? So you have, let's take your choice as a polynomial, an elliptic curve with like z coefficients. You can look at its finite field solutions. You can also look at its complex solutions. And if you look at its complex solutions, then these pi are reflected. Pi is reflected by the ith Betti number. So the ith, the rank of the ith cohomology, which is also, the rank is also something that's called a Betti number of xc. Of course, some conditions need to be met. There is some notion of like a good reduction. There are some nuances that I don't want to get into, but broadly speaking, sweeping many nuances under the rug, PI is something that deeply captures cohomological information. If you are someone who has seen a bit of other variations of cohomology, like étale cohomology, then this is, I'm just going to write down the formula just to have it on record. If this doesn't make sense, don't worry about it. Okay, so that's a lot of letters. I'll just say a few words. This is the étale cohomology that people have started to care about since the Weil conjectures for very good reasons. If you don't know what that is, think of singular cohomology if you know what that is. This FROB thing here is the fact that there is something called a Frobenius morphism, where you have, suppose you have like FQ solutions, you can raise the solutions to various indices, and that reflects a transformation, a linear transformation on cohomology proofs, and you can take the trace of that. And this is what that object is. There should be a TR in front just to denote the trace, but too many parentheses. And this T is just the indeterminate variable. And this is exactly the thing that Weil was hoping for, that there should be some cohomology theory that completely explains how algebraic varieties, both over complex numbers and over finite fields, can be studied on the same footing. So in conclusion, so here is what Weil said, and this is literally quoting Weil: the proof, back then these were just conjectures, the proof must be cohomological. And Grothendieck, and this is not quoting Grothendieck nonetheless. Yes. So Grothendieck answered an emphatic yes and developed the whole branch of étale cohomology. Dwork proved the part of the conjectures which is about the zeta function being a rational function, And then Deligne did the rest about like Riemann hypothesis and such. And so conjectures are no longer conjectures, but they are famous or infamous enough that they are still called conjectures. Okay, so it's 10. I'm just going to take a couple of minutes to sort of like conclude the talk, and then I'll leave it up to you to ask questions. So finally, curtain call. No boundaries. Um, so bridging the apparent divide between something continuous like the complex solutions and discrete like, say, finite field solutions is is fundamental to the unification of seemingly disparate part of mathematics. Or at least at that point, they were disparate part of mathematics. And this bridge is formed by, since we are at the end of the talk, I can just throw in a bunch of like cool buzzwords for you to look up and think about. Um, XZ is somewhere in the middle. Um, and the things that come up often in this context is this. You may have heard of mixed Hodge structures, which is something that is very typical of these continuous guys, but says a lot about discrete things as well, if it's studied appropriately. And possibly the biggest part of this bridge is the deep and astounding theory of motives. It's quite fashionable nowadays to talk about motivic cohomology, motivic homotopy theory, motivic, the category of mixed motives, blah, blah, blah. You might feel very motivated about motives. The motivation behind motives was the goal to sort of unify all these geometric objects and study them in a way, study them on the same footing. So in this dance, in this dance between topology, geometry, and arithmetic, we see that the boundaries are entirely superficial. Well, we see now, but Weil saw back then, and never so firm after all. Thank you. Questions? I cannot hear anything, so I would assume there are no questions.
Uh, if there are no more questions, we can wait for some time and see if no questions.
Sure, no problem. We can wait 5 minutes.
I can see a question in chat. So Manpriam
What
asks,
are motives?
yeah.
Okay. Uh, so motive is sort of encoding a geometric object, let's say a variety or a scheme, in a way so that you wouldn't be specifically thinking of it as its complex points or specific field valued points, but rather you would be thinking of it as an object in its own that you can sort of transfer across various fields and get information out of that. So it's sort of like thinking of um, here's an example. If you know what a projective space is, uh, you can write a projective space as as an affine space plus a point. And to write that, you do not need necessarily the complex numbers or the real numbers or a finite field or FQ bar. So the intrinsic properties of geometric objects that carries through different fields and gives information as you need is something that was uh, captured in that Grothendieck wanted to capture in the word isn't supposed to be motive. Like historically, Grothendieck's uh, Grothendieck's terminology was a motif, as in like a picture, a motif, and it was pluralized and got into English language like that and became motives. So it's not about motivation per se, as motivating as it sounds. It's about the sort of the intrinsic picture um, that's there, regardless of sort of what ring or field you're working on. An analogy should be something like once upon a time, people used to think of geometric objects as, say, like cut out by as like graphs in graphs of functions, but or like cut out by equations and graphs of functions in sort of like a Euclidean space or something. Then later on, we learned that those are embeddings of intrinsic geometric objects. Like you can write a sphere as like distance one from the origin in the Euclidean space, but a sphere exists in its own right, and you're embedding the sphere in the Euclidean space in various ways. So this sort of like extracting the fundamental out is something that motivated Grothendieck to coin the term motive. And yeah, so there are ways to define a category. So in the complete generality, the category of motives is not really something that mathematicians have been able to define yet. It's a big problem that people have been really thinking hard for the longest of time. But there are some incarnations of like what is called category of baby motives and such. But like essentially the idea is that you would be able to write such things in those categories where you do not need to necessarily have a C here or a FQ here or a or R here or a Q here, like rational numbers, etc. This sort of relation holds sort of regardless of what base you're working on. So you can draw a finite field line and a projective line with a 1-point compactification, except that 1-point compactification is not something that you would be able to talk about when you are just working on finite fields. Nonetheless, Grothendieck's motifs have made that reasonably possible in a reasonable sense. Does that answer your question a bit?
Yeah.
Thank you.
Thanks, Shri, for your wonderful talk. Uh, so
No,
yeah, so we'll wait for some more questions and then we'll recommend.
sounds good.
Okay, if not, probably we can end it here. Thank you once again for your wonderful talk. Yeah,
Thank you. Thank you. The pleasure is mine. Thank you.
bye.